Okay, so it's a great pleasure to introduce Professor Karthik Padabirman from University of British Columbia. Karthik got his PhD in 2009 from the University of Illinois in Champaign-Urbana, and he spent a year at Microsoft Research working with me as a postdoc in 2010. Since then, he joined the faculty at the University of British Columbia and has worked in the areas of resilience, security, JavaScript, web programming, and today he's going to talk about two interesting topics. One is IoT and the issues around building secure and reliable IoT systems. The other is looking at systems built on top of neural networks and how understanding the resilience of those systems is very important, especially in the growing areas in which they're being applied. So with that, thank you very much, Karthik.
Thank you, Ben. Thank you, everyone, both who are listening online and who are here. So it's great to be here. As Ben mentioned, I was a postdoc here about 5-6 years ago and have very good memories. So I'm going to be talking today about a couple of recent projects we've been doing in my group. My background is mostly in fault tolerance and security. And this is applying classical fault tolerance security techniques to two emerging areas, self-driving cars and smart devices. So this is joint work with my PhD students as well as collaborators from NVIDIA research. So my research broadly is on building error-resilient and secure software systems. So work on three broad areas, on software resilience techniques, web applications and JavaScript programming, and recently on cyber-physical system security. I'll talk more about this in this talk, but the focus here will be cyber-physical system security and resilience. So what are cyber-physical systems? So these are systems we interact with on an everyday basis, or the more modern avatar, which is IoT. So if you look at a modern car, for example, it's mostly a computer that that controls many of the essential functions. So for example, when you press the brake pedal at a certain speed, it's an indication to the computer that you want to slow down. There's no physical hydraulics anymore, at least in most cars. Smart meters, many of us have these in our homes. They're also powered by embedded microcontrollers. That's a Nest thermostat, which is recently acquired by Google, but there are many other such devices as well. And of course, embedded medical devices in the human body. So these are examples of cyber-physical systems which have to interact with the environment. And as a result, their safety and security is extremely important. So that's the good news. So unfortunately, the bad guys are never far away, so to speak. So there are a lot of security and reliability issues that come to the fore. So perhaps the most well-known is the hack on the modern car. These guys with Wired magazine, they were able to attack a car that was going down the highway. There's been work from UW on smart pacemakers and smart medical devices. There's also been tons of attacks on smart meters. I won't attempt to list them all, but people have shown that pretty much you can make your smart meter read whatever you want, including negative values of power consumption, if you like. And with the Nest thermostat, I don't know of any attacks, but there was a famous glitch, I think, in January 2016, where it went down and after a software upgrade, and pretty much the temperatures hurtled below. This is in the dead of winter. So it's not just security of these devices, even the natural failures are very important. So with that said, how different are these systems from regular desktop or laptop computers? So there are a bunch of challenges that are unique to cyber-physical systems. So first is many of these systems operate under real-time constraints. So for example, in a pacemaker, I mean, that's an extreme example. You have to deliver a pulse every 1 or 1.5 seconds. But many other systems also have similar real-time constraints. Like in your brake, when you hit your brake pedal in your car, you better convey that information to the computer within a certain amount of time, or else you might hit the car in front of you. So there are these constraints. There are also resource constraints because a big fraction of many of these devices are extremely resource constrained and they're very cost sensitive. So to give you one example, a typical smart meter costs a few $100s. Even adding some extra memory on that would actually increase its cost by 10 to 20%, so which many of these manufacturers don't want to do. So likewise, in a modern car, I've been told the compute is at least 20% of the cost, especially when you move to self-driving cars and so on. So these are cost constrained as well. They're hard to upgrade because they need to operate continuously, often in remote environments, so you can't restart them on an ongoing basis. And often there's no human in the loop, right? So you can't ask for confirmation of an action, or when the system is dealing with an important event, like a life-critical event, you can't have a human say, is this the action they want to do? So that's the other challenge that comes up. So with that broad motivation, I'm going to be focusing on two specific systems in this talk. So one is we're going to look at some work we did on resilience of deep neural network accelerators employed in self-driving cars. And here we are focusing on soft errors or hardware faults which cause single event upsets or bit flips in these systems. And in the second part of the talk, I'll talk about intrusion detection systems for smart embedded systems for which we use dynamic invariant detection. Technique that's been used in software engineering, but here we adapted it to cyber-physical systems. And then I'll talk about some of the ongoing work in my group around this theme, as well as some conclusions. So I don't need to stand here and tell you that self-driving cars are big. They're, depending on who you ask, they're either 5 years in the future or 15, but everyone acknowledges at some point they'll be here. Big companies are investing a lot of money into this. But more broadly, one of the main technologies that make self-driving cars possible is deep neural networks, or the ability to recognize other cars, pedestrians, etc., and take action accordingly. So this is definitely a safety-critical application. Nobody wants to build a self-driving car which is only partially correct. So these are. It's very important that we get this right. Another important constraint here is their real-time constraint. So you want, for example, your car to look at the image and then classify it appropriately within a fraction of a second or within some time-bounded period so that you can take action. So what many of the companies in the space have been doing is investigating specialized accelerators, hardware accelerators that they can deploy on these self-driving cars, so to run deep neural networks. Now, there have been other instances of accelerators for deep neural networks as well, like the data center space. I'm not going to talk about it now, but many of what I'm going to present today, many of the results also apply in that space. Now, why do we care so much about self-driving cars in particular? So I'll show you examples where even a single bit flip can actually cause misclassification. But more importantly, in this particular space, there's very strict regulation. So you have to make sure, or you have to prove that your chip has what they call a fit rate of failures over 1 billion hours of less than 10 overall. And this is for the entire chip, not just the DNN part. So these are standards. So the ISO 26262 enforces this. And if you're a company that manufactures chips for these cars, the onus is on you to show that you meet that standard. So it's a very real problem. So this is regardless of any other source of error, you've got to show the fit rate to be within that bound. So one of the big challenges in modern electronics is soft errors. So where you have alpha particles or cosmic rays come and upset your transistors and either lead to charge deposit or charge depletion. So I won't go into the device physics of this. But what happens is if you have some electronic component, like a adder, for example, or a multiplexer, what you might end up doing is getting a wrong bit on it. So it's 0001, here you get 0101. Similar things apply to flip-flop storage elements as well. But from a high-level programming perspective, these manifest as value corruptions. And there's been numerous instances of soft errors actually affecting business-critical applications. The famous one being Sun had to recall their servers, things back in 2001, and it made the front page of New York Times. And there were other similar events that actually caused bad publicity as well as losses of billions of dollars. So these are things that chip designers have to worry about. Now, I'll show you just one graph here. So soft errors have been increasing in computer systems, at least for over the last decade or so. This is a graph from Shaker Borker. The x-axis is the feature size, or the number of nanometers we're using today, or like 16 or even 8 nanometers. And the y-axis is relative units. So these companies never tell you the actual error rates. They show you relative error rates, and you can see that's going up exponentially, right? So this is a real problem, and it's going to get worse as we integrate more and more electronics on the chip. Now, you might stand there and say, haven't we solved this problem? Yes, Ben, of course. Yeah. Oh, sure.
So if the error rates are going up like that anyway, even independent of the DNN stuff, how are they protecting the card chips now, right? Because it seems like it's, they have to be some strategy because of this.
Right. So that's a great question. In fact, that's the my next slide. So today, what happens is they guard band it. So they say, okay, I'm going to. I know that at this voltage, the probability of it actually flipping the bit is very high. So I'm going to engineer double the voltage, for example, right? Or they do things like I'm going to replicate certain parts of the pipeline with DMR, and I don't necessarily think those are panaceas, but they might work for more traditional CPUs where you have a larger power budget and performance budget. In the DNN case, this incurs high overhead. Another strategy is ECC or parity on all storage elements. So they have real-time constraints. So you can't go replicate your critical path, for example. Another thing people have tried to do is there's been a lot of work on generic microarchitectural solutions, but these are DNN algorithm agnostic, and they end up being non-optimal for these systems. Especially to give you one example, a technique we've developed and other researchers have developed is selectively duplicate the computation. So figure out which parts of your program are really influential to the output and then duplicate that. This doesn't really work on a DNN because the actual program is like 5 instructions. So you duplicate it, okay, well, you pay 100% overhead or very high overhead. So these are very different beasts from your traditional programs that you run on regular CPUs and so on. We do have other work in my group looking at how to protect programs running on CPUs as well as GPUs from soft errors. I'm not going to talk about that today, but however, there are similar challenges in that space as well. So a very brief overview of a deep neural network. I'm not a machine learning expert, but this is sort of my understanding of this. So you have multiple layers in your neural network, and in each layer has specialized functions. So you have an image, you feed it into the first layer, and it goes and classifies it into one of many categories. So there are different feature maps. There's a convolution layer, subsampling layer, and so on. And different neural network architectures have different combinations of these layers. So when I get into the details of the experiments we did, I'll talk about which sets of layers we considered. And the other side of this is, so this is from an abstract level, but the accelerators actually have an architecture that lets you implement those layers directly in hardware without going through the software. So there is, the software simply says do a convolution, but that operation is done directly in the hardware. And the way they do it is they have this array of processing elements. So this is an example of an architecture from MIT called IRIS. So they have a global buffer in which goes to the DRAM. So that's where you fetch the data, and then the data gets streamed to these processing elements. So it's almost like spatial computation. Again, yeah, you have a question?
Like the TPU, the Google?
Yes, it's very similar. Thank you. Yes, so many of these have very similar architecture. Yep. In fact, I believe in the architecture community there are at least a dozen of these variants that people have proposed. We're looking at one particular one, which is IRIS, but our results are not confined to this. So we try to canonicalize the architecture here. So we try to make it as generic as possible. And what a yes, sure.
Are these already products, or they are pretty much still in the research phase?
Okay, there are some products out there. Okay, I'm not allowed to say anything about the specifics of the NVIDIA architecture, but Google already has TPU, as you know, and there are other such architectures as well. Okay, but what we are doing is using an open source architecture called IRIS, which was proposed to the research community. So anybody can go and play with it. So it's a processing element. It's an array of processing elements, and processing element is basically encoding these operations directly in hardware.
So is IRIS actually a chip?
Yes. So they have. So Joel, who was one of the co-authors of the paper, so his group at MIT, they released the chip and they measured its power consumption, etc. Okay. So there have been a couple of others. There's this. There's a group from China where they also have a similar chip for doing DNNs. So they're not the only game in town by any means, but it was as good as any of the other architectures. And one of the things they have going for them also is they can do dynamic reconfiguration on the fly. So they claim at least the goal is to have more adaptivity, unlike some of these others where once you fix the architecture, you're stuck with that. So again, I'm not a chip designer, so I can't speak on the merits or demerits of IRIS versus other architectures, but I'm told it's fairly typical of many of these DNN accelerators. So the goal here, what we are trying to do is understand error propagation in DNN accelerators through fault injection. So I'll tell you what we exactly mean by fault injection. Second, we want to both quantify the error probability as well as characterize it. And of course, we want to mitigate the failures, right? So the goal is to gain insights so that we can come up with efficient ways to detect errors. And I'll tell you later about some hardware as well as software techniques we develop to go and detect these faults. So what is fault injection? As the name suggests, we go and perturb different values in the actual implementation of these neural networks on the chip according to a fault model, and then we study the effects. So we consider 4 neural networks here: ConNet, AlexNet, CafeNet, and NIN, and the data sets are given as well. So these are fairly standard in this community. So there's a whole bunch of input data sets that they come with, and the number of output candidates tells you how many classes they classify the result into. There are different ways of implementing these neural networks. You can use fixed point as well as floating point. So we looked at all these data types. So we looked at 16-bit as well as 32-bit fixed point. So to give you an example, a 16-bit fixed point has 1 sign bit, 5 integer bits, and 10 fractional bits. So you can probably tell that. But and 32-bit, I'll be more specific about what we exactly consider when I present the result. And likewise for floating point. So these are being proposed by researchers in terms of saying for certain neural networks, certain data types are better. But we look at the whole gamut of it. So how do we do the fault injection? So we actually inject 3,000 random faults in each latch, in each layer of the neural network. So we mostly consider faults in sequential elements because this is the dominant fault model today. We use a simulator. It's called TinyCNN. It's written in C. And what we do is we emulate faults that occur in the hardware into the C code. So an example would be, okay, this is very simplified code. It says for each layer, for each weight, for each input. So instead of actually doing the computation there, we would go and inject a fault using our function. Okay, we've also verified that this corresponds to the result of beam testing experiments. The places where we inject faults are places where real faults were observed when we put these under neutron beams. So we built this fault injector. We consider a single bit flip fault because that's the dominant fault model for transient faults. We also consider faults that occur in latches in the execution units as well as storage buffers like SRAM, scratchpad, and register. So in a nutshell, we inject faults in pretty much any sequential element in the chip, and we do this multiple times, 1 fault per run, to get statistical estimates. So before I tell you about the results, let me sort of put up the mandatory slide on what's the consequence of a silent data corruption, as we call it, where some data gets corrupted. So this is from a real fault injection experiment we did. Okay, we did found many such cases, but this is an illustrative one. So the neural network was supposed to classify this truck, of course, as a truck, but it ended up classifying it as a bird. Now, depending on we didn't actually put this on a real self-driving car, so I don't know what really happened, but my guess is if it sees a bird, it's not going to slow down, right? So that could be a problem. So we found many cases where a single bit flip can actually cause the whole DNN to be misclassified. Yes, sure.
So you not only inject into the first layer, there is possibility that you inject the bit flip the very last moment when they try to output the classification.
It is possible. So we try to be random here, right? So we pick. So if you're let's say if 99% of your time is being spent in the first few layers, then there's only 1% probability will inject into the last layer, right? So we try. So we want to emulate what happens in reality. So the layers are getting executed on the on the accelerator. So any of these could actually be subject to faults. However, I'll show you later the distribution of faults by layer, and you'll see that some of the results are surprising.
Because this single evidence may not show that the probability of this.
That's true. So this is just anecdotal. I will show you data which looks at the distribution by layer.
Yeah. Another question is, can you go back to
sure.
So I guess I don't miss something. I missed the connection between the C program and the chip.
Oh, the C program is just an architectural simulator. So all I'm trying to say here is we do the injection in the architectural simulator. You can think of it like simple scalar for CPUs, right? So there is a DNN simulator, acceleration simulator here, and we identify which parts of that simulator actually map to the hardware, and we know those parts that are susceptible in hardware, and we inject the fault in the simulator. I mean, this is just a way for us to do the fault injection without having to twiddle with FPGAs and the like. Does it answer?
So this C program is not very specific to this kind of chip.
No, it's not. So we had to do that mapping.
High level thing.
That's correct. But we did the mapping and we've also validated it with neutron beam results. So whenever companies release a chip, they put it in a neutron beam to see where errors occur. And so to first order of approximation, we know these are places where errors occur, right? But of course, with all abstraction, we do lose some information.
So go to the next slide. Just,
Yep.
So one of the things about it is that the classification loop, just like any real-time system, it's going to reclassify presumably.
Yep,
So how does that affect the ability to actually, decide that's a truck? Because one frame out of 100 or whatever, it's saying it's a bird isn't so bad, right?
Well, okay, so that's a good point. Right? So it depends on the speed of at which you classify. So typically, I've heard numbers from 0.3 to 0.5 seconds for each reclassification. Depends on how fast the accelerator is. Now, this is for this particular platform, right? But think of it this way: if you're going at 70 miles per hour, you have half a second to slam on your brakes, so that by the laws of physics, your self-driving car comes to a stop, right? Depending on the distance to the object. So I'm not claiming that all of these will result in collisions or even at once, but so again, let's go back to the standards. So the standards say that if you have a failure like this can occur no more than 1 or 10 every billion hours. So that's 10 fit for a whole chip. So even if maybe you are lucky and this didn't actually cause a collision, you'll still fail to meet the standard if you don't actually guarantee that. So that's at least the goal we have set here. Do you have a question? No? Right. So we asked a bunch of research questions here. So we said, what are the silent data? So I should have mentioned this. So silent data corruption is a standard term we're using for measuring when the output actually differs from the correct output under a fault injected run. I'll tell you more about how we actually determine whether something is silent data corruption or not. So we looked at what are the SDC rates in different DNNs for different data types. And then we looked at sensitivity on a bit level basis, so which bits are sensitive. And then we looked at the actual values themselves, how far they are from the correct values. And then the question you asked about how the errors propagate layer by layer. We'll look at that as well. Yes.
So on a like orthogonal axis, there's also, you talked about the different precisions of floating point.
Yep.
Do different precisions of floating point result in different classifications?
Hold that thought. I'm going to talk about that. Okay, that's I'm coming to that. Actually, in fact, maybe just to give you the short answer is yes. Yes, by a significant amount. Okay, and we'll see how. But before going further, we should define the kinds of silent data corruption. So let us keep in mind that a DNN is not like not like a typical program which outputs one answer, right? So if a bit is off in that answer, you can say, oh, the program was wrong. Here, it might output the answer that's acceptable regardless of whether or not that's the correct answer. So we call the first kind of SDC, what we call SDC1 is, you have a mismatch between the winner, the top ranked answer, from the correct network to the faulty one. Then we looked at the SDC5, which is the winner is not in the top 5 predictions. So you might argue, look, if it says even in one of the 5 predictions it's a truck, it should stop, right? So we looked at how far away that was. And then we do the same thing for 10% and 20%. So the confidence of the winner, so the neural network also outputs a confidence saying I'm 90% confident this is a truck and 10% confidence it's a bird, right? So if the confidence drops by more than 10% and 20%, that's also an issue because now essentially you don't know what it is. Or many of these things have thresholds that say, for example, for me to apply a braking action, I need to be 90% sure there's an obstacle in front of me. So that's the threshold we are working with. So I'll explain the graph, but first I just want to show you the overall trends here. So the x-axis is the different kinds of precision, double, float 16. 16 RB10 is when you have a 16 bit fixed point, but you have 10 places for your for the mantissa and 5 places for the exponent, or 5 bits for the exponent. And 32 RB10 is when you have 10 places for the decimal and up 21 places or 21 bits for your exponent, and so on. So we also looked at the different kinds of SDCs. So SDC1, SDC5, SDC 10%, SDC 20%. And one thing that stood out, and the bars are the different, the different shadings of the different neural networks. So one thing that stood out across all of this is that the 32RB10 has a very significant SDC rate, as you can tell, right? Without even looking at the specifics. So this is because some of you might have guessed it already. You have 21 places or 21 bits for the exponent. So one of those gets hit, you're going to cause a large deviation, and you're going to result in complete misclassification. You can't tell from this graph, but I'll show you in the next graph, that the actual data type, even between float and float 16, etc., actually makes quite a lot of difference in terms of the sensitivity, as does the kind of neural network layer. But the takeaway here, at least from a high level, is that you see that there can be actually significant amount of state exposed when you're using these wide data types, and that can cause high SDC. Another thing also you might notice is that there's actually not that much difference between the different SDC types, despite what I said in the previous slide. We looked at all these different kinds of SDCs, but we found that actually they don't matter much in practice, the difference. So from now on, we said, okay, we just go with SDC1 because it seems like the results are similar. And intuitively, why this is the case is if you have 1,000 possible entries, let's say you have a random fault, okay? Something just randomly misclassifies it. The chance of that random misclassification being in the top 5 out of 1,000 is actually very small. So whether it's the top 1 or the top 5 or the top, the confidence being less than 10%, that's not such an important metric. Yes?
Just to understand, why would you design a thing that had 21 bits of exponent? That's a giant range that you're expressing relative to the number of bits in the mantissa, right?
That's an excellent question. So one thing is many of these DNN accelerators, they're designed to be general as possible, right? So you don't want to be, so if you didn't accommodate that, you don't want to be stuck with the choices you made. So one of the takeaways we're going to get to is that it's better to restrain a data type as much as possible for the specific DNN you're trying to run, rather than make one accelerator to rule them all. That's very general because this gives you this large amount of bit space that can go wrong, right? So in fact, that goes to the second question, right? So we looked at how sensitive are the different bits, and on the top you see for the exponent bits and for the floating point data types, and for the fixed point data types again for the bits that encode the exponent to the other side of the binary point. And at a very high level, the exponent bits are the ones that are very sensitive to errors, as you would expect, because an error in the mantissa, no problem, the neural network is resilient, it will converge. But you have an error in the exponent, and we look at exactly what kinds of errors those are in a second, but that can lead to large probability of silent data corruption. So again, this reinforces the result that you're better off designing your data types to be exact or as close as possible to the dynamic ranges of values. Yeah, and no.
You're saying that it means your data space should really be small in the sense of not spanning a lot of orders of magnitude.
That's correct.
And is that easy to do for neural networks? Do they tend to have that property, or are their values tend to be?
Okay, that's actually an excellent question because that's the next question we investigate.
Yes.
But I'll give you the high level. So not always, okay? But it turns out in most of these cases, the values cluster around 0. So there have been other studies of theoretical analysis of neural networks where they show that the values eventually converge around 0, and the further it deviates from 0, the higher the probability that you're going to get a wrong answer. And that's exactly the intuition here. So this shows, so these graphs show the neuron values and the probability of a silent data corruption. The reds are the faulty ones, the greens are the correct values. So this is with float 16, and these are for silent data corruption. These are the ones that result in benign. So right away, even without perhaps squinting too hard at the graph, you can see that for the silent data corruption ones, the values are actually go all over the place from the correct value, right? The correct value is near 0. So the further you cause deviation from 0, the harder it is for the neural network to converge, and as a result, you might end up with a silent data corruption. Whereas the distribution is more even in case of benign, right? So you don't get this runaway effect, so to speak.
My question was, without errors, does the neural network, for its correct functioning, require that? So you're saying at convergence they get towards
right, yeah, okay.
At the beginning, do you need these values that are so many orders of magnitude away from zero?
I see.
You just say like I'm not going to have any exponents, like my
Right. So the answer is neural network specific. So there's been work, for example, in the architecture community that looks at the power consumption for different dynamic ranges of these values. And one of their conclusions is also to keep the power consumption low, you've got to learn the characteristics of the neural network and design data types exactly to fit that. So there is some. So what this argues for is more specialization rather than make it a general accelerator platform. So if I know you're going to run neural networks which have small dynamic ranges, then I should try to pick my data types to fit those dynamic ranges.
There are a lot of neural networks that do have these narrow ranges.
Yes, that's correct.
Okay.
So as a designer, you have the choice to use those networks. Of course, they may take longer to converge or they may be slower, but that's good for both energy as well as resilience. So that's the message here. Right, but yeah, thank you. But for this graph here, it's only the 40 distribution. It's not the correct value distribution. I'll actually use this result later also to design what we call software, symptom-based detectors, which are in software, where you can dynamically bound the range of these neuronal values. So if it's outside that range, chances are it's going to be a silent data corruption. So you stop the error from propagating. So we'll look at that in a few slides. Now looking at the distribution by layer, I apologize for the quality of the graph there, but it's in our paper as well. So what we do is we have these three neural networks, AlexNet, CafeNet, and those are more or less in a similar range, and ConNet. One thing I should have mentioned earlier is ConNet doesn't have what is called the renormalization layer. So these networks do, and you'll actually see the effect of that. So you see at least AlexNet and CafeNet do. So you see when you have the fault in the first two layers, which are doing the normalization, actually the probability of it being a silent data corruption is very low because it's bringing the value back to the acceptable bound. And after that, if you have a fault, it keeps going up. And the reason it spikes towards the end is the last two layers are fully connected in this network. So you have one fault that's going to get spread everywhere all over the place, and maybe that's where that particular example is coming from, where you have a fault in the last layer, or the later layer, it's going to get spread, and there's no renormalization to bring it back. Whereas in the NIN case, actually there is a normalization layer towards the end as well. So that's another lesson you can learn from this, right? So you might help to actually put normalization layers towards the end, so you bring the value back to an acceptable range rather than spread it all over the place. Now, one other thing also is you probably, as you keep increasing the layers, your probability of a silent data corruption increases. So a fault early on may not matter as much. A fault later in the execution may be much more consequential. The same graph you can see with the Euclidean distance of the values. So we measured the distance between the value, correct value, and the faulty value for the different networks. And again, you see in AlexNet and CafeNet, the Euclidean distance actually drops quite sharply around layer 2 and then stays there. Whereas these other two guys, the value can be quite significantly different. So the idea, again, there's one thing to take away here, that the further you go from the convergent value of 0, the higher the chances of SDC, and you want to put layers that actually bring that value closer to that. So the local response normalization, or LRN layer in layer 1 and 2, renormalizes the value back towards the normal range. And then, so you want to put such layers in your networks, if at all possible, to keep the value bounded. So now you might say, okay, what is the use of all this? What if I don't really have ability to choose the neural networks I want to run? Is there anything as a as a chip designer I can do to mitigate these faults? So one thing that's that you can do is you can choose narrow data types. So for example, you can choose 32B RB26, which is you have 26 bits for your exponent the mantissa, and just 5 bits for the exponent, rather than this other one where you have up to 21 bits for the exponent, because that can vary widely. But then you can say, how much difference does it actually make in practice? So here we have to use some projections, because the IDIS architecture I talked about was fabricated at 128 nanometers. So we want to look at the effect on 28 nanometer, which is the current technology, or even lower. So we used some results from a paper in nuclear engineering where they did these neutron flux measurements and scaled it down. So had collaborators who knew this, not not me personally, but what we ended up doing was to project the actual the fit rate for these different architectures. And as it turns out, if you use the wider data type, your fit rate can be about 60 just for the DNN accelerator. And this is a problem because remember I told you the fit rate has to be less than 10, right? And that includes whole chip, not just the accelerator. Whereas if you're judicious about your choice of data type, you can actually bring it down quite a bit. So here's an easy fix, right? So you can choose the data type that actually fits the neural network you want to implement and bring down the fit rate by almost an order of magnitude, right? From 58.2 to 5 point something. So this is one easy thing you can do to keep the values restrained. But what if this wasn't enough? What if you had other parts of what if you wanted to bring the fit rate even lower? So here we are proposing symptom-based error detectors that can be done in software. So at the end of each layer, you can check whether the value deviates from 0 by a significant amount and detect that. Or you can learn the correct ranges over a period of time, and then you can run the range check so that if the value deviates too much from the correct one, then you're going to stop the network from computing. And we find that if you did this, you can actually, it's a fairly simple range check at a very simple level. And the recall of this can be about 93% with 90% precision. So you can actually bound the ranges fairly tightly and they're fairly predictable for the class of neural networks we studied. So this is something you can do in software. If you want to be even more sort of, you want to guarantee your fit rates are bounded, you can also do things like selectively protect certain latches in hardware. Of course, this assumes that you are the designer of the accelerator platform, so you can decide which latches to duplicate. So the sort of the baseline would be duplicate everything, but that leads to huge overheads. So here we say for a given flip-flop target rate reduction, what is overhead? And TMR is triple modular redundant, where you duplicate everything 3 times, and there are a bunch of other strategies here. And the important thing is the curve has this reverse exponential kind of distribution here. If you look at this fraction of predicate latches, so by protecting about 20% of the latches, you can bring down a fit rate by 80%, right? And of course, to get to the last 80%, you've got to pay the rest of the cost. So this is an important result because it means that you can go after the low-hanging fruit and get pretty big wins. Yes, you don't get 100% protection, but you get 80% of the fit rate reduction just by protecting about 20% latches. So you don't have to duplicate everything, for example, because that has its own attendant costs. So this is based on a theoretical model that one of my co-authors derived. So we've tested this on regular CPUs, but this is still something we're testing on the DNN accelerator platform because we have to go and refabricate the whole chip to incorporate this. So, but the takeaway here is with 20% overhead, you can get almost 100x reduction in the fit rate. So what we did in this project was we characterized error propagation in DNN accelerators. We looked at different parameters, data types, layers, value types, and DNN topologies. And presented 3 mitigation methods. I'm not saying these are panacea, but these do bring down the fit rate considerably. So things like restraining the value range of the data type, if you can do that, depending on your neural network design, adding a value range checker, and we show that you can do this with pretty low overhead in software, and selective latch hardening if you actually are able to modify the hardware. So the takeaway here is if you can adapt your fault tolerance technique to the characteristics of the application or the neural network, you can get much better protection than the generic one-size-fits-all approaches. So your question?
So the value range checker, so is your proposal there is it dynamically determining what the right value range is?
That's correct.
Is that in hardware? Is that?
It's done in software because at the end of each layer you can look at the output values. So you're reusing the same hardware for each layer, right? So you read back the values in software, and then you can we added the checks in software.
Okay.
And in fact, you can use the CPU to do the checks because the CPU is sitting idle while the DNN accelerator.
Okay.
Yes. When you say neuron values, you mean those values after each layer?
After each, the output of each layer.
But not the temporary variables.
No, not the temporary. The output of each layer. Well, I don't know if you want to they are temporary if I look at it, if I look at the neural network as a black box, right? But they are the values that are produced that are featured.
Between two layers, there are variables.
Right, so those are the ones I'm talking about. The output of each layer.
Do you want to put a range for that?
That's what we do actually. We learn the ranges of the outputs of each layer. But in between the outputs, there are other temporary variables which you don't care about.
Okay.
So for us, when I say output of each layer, I mean the actual values communicated between the layers, not just the ones at the end of the neural network.
Right.
Right. Thank you. Any other questions about this part? Okay. So now I'm going to tell you about something that is actually quite different, but has the same theme, which is that we want to build intrusion detection systems for the cyber physical systems, and we're going to use dynamic invariance here. So the motivation here is we want to provide low cost security for cyber physical systems. So we want to satisfy resource as well as real time constraints, no human intervention needed, and we want it to be able to detect zero-day attacks as far as possible. So we don't want to be having to upgrade our signatures in the field for these devices and so on. So we want to, as much as possible, make these systems be autonomous and capable of running intrusion detection software on their own, on the host, without relying on a network connection, for example. So here we're going to leverage the properties of the cyber physical system. So we're going to look at, so most of the cyber physical systems we consider have timing predictability. What does this mean? They have to send a message every X seconds, or they have to send a pulse. They have to do this loop within a minute, for example. So there are timing constraints that are part of the specification. And we're going to exploit this and use time as a first class constraint to detect intrusions. And so then the idea is actually straightforward. We learn the invariance based on the dynamic execution, and we monitor these invariants at runtime to see if they are violated. So, so let me sort of tell you a little bit about the threat model we consider. So this is a model of the cyber physical system. There's a communication network, a physical process, and a cyber process, which could be a control algorithm. And the physical process is sending its measurements to the cyber process, and it's sending actuation commands. So we are looking at attacks. So attacks can occur at any part here. It can occur in the cyber process, in the physical process, or in the command send. So we are not looking at attacks in the physical process. So if you attack the physical process, we learn the wrong values. But what we are doing is we are trying to learn the invariance from the cyber process and use these for intrusion detection. So a very simple example would be, let's say this was a smart meter, or let's say it's a car, and you know that your current value of speed can't be greater than the previous speed value by more than a certain threshold. So this is an invariant you could learn, so that if there is an attack that tries to compromise this, you would be able to detect it. So of course, we are not the first to come up with intrusion detection systems. There's been a ton of work here. So the classical ones are signature-based IDSs, where you have to give it a bunch of attack signatures. These don't quite work for these systems because you need to update the signatures on the fly, and you want the ability to provide zero-day attack detection. And then there's also work on anomaly-based IDSs, where you learn some statistical models of the behavior, but those have false positives. And there's other work that's shown that these are less than suitable for these systems because you don't have a human in the loop that you can alert when there's a false positive. Having said that, what I'm going to talk about is also related to that, so we'll come back to that here. Then there are specification-based IDSs, where you learn a specification of what the software is doing, and then you try to detect attacks. So you can do that through static analysis. But unfortunately, in these cyber physical systems, there's a lot of interaction with the environment. A typical static analysis doesn't capture this unless you go out of your way to model the environment. Right? So what we are doing is we are going to use dynamic analysis. So we're going to learn the invariance by monitoring the system over a period of time, and then use the invariance to go and detect attacks. So this is the sort of modus operandi. So what's an invariant? Many of you are probably familiar, but just to give examples, so you could say energy usage should be greater than or equal to 0, or the current minus the past value should be less than or equal to threshold, or some other sequence of values should, some other value should fall into a certain sequence, and so on. So there's been a lot of work on dynamic invariant detection in the software engineering space. So starting from DICON, from UW, and there's been work on Texada for distributed system, Perfume for mining properties of reactive systems, and so on. And the common thing with all of these systems is they look at only one of two dimensions of data, time, or event. So if you look at events, cyber-physical systems are going to send, receive messages, and those are events, for example. Time, of course, what is in data is just the data values that are changing, right? So if you look at DICON, for example, which is one of the classic dynamic invariant detection systems, they only looked at the data, how the data actually changes, right? There's other work that's looked at just the event patterns, or looks at events and time. And our insight here is that you actually need to look at data, time, as well as events, the interplay between all these three, because that's really where some of the interesting attacks are going to try to break your invariance. And I'll give you an example later, but in a nutshell, what happens is, in these cyber-physical systems, there have to be predictable data value changes at certain times. And we want to be able to learn those invariants, and if you try to either change the value prematurely, or you don't let the value change, or you suppress an event that's supposed to occur at a certain time, then we will detect that. Now, this will not work for a regular general desktop computer because you don't have that level of timing predictability in a typical application. But the applications that run on these devices are simple, and they follow this kind of repeated patterns. So that's the secret sauce, if you will, that lets us actually go and detect these invariants. So if I look at data, event, and time, so one way to learn these invariants will be to simply look at all these three variables and navigate that space. The problem is, however, this leads to state space blow-up, because this, almost every pattern you can think of, you can learn between these three dimensions. So the insight we are going to leverage here is, I can actually look at data, event, and time conditioned upon the event space. So cyber-physical systems are very event-driven. So there's usually a explicit command. So if you go back to the slide I showed you, where you're sending a command to a physical process, getting measurements, each of these is an event. So you're reacting to some external event. And the idea is, I can break up the space by events and learn the data values that has to change, as well as the time properties of that event, so I can use this to come up with the invariance. So the system we built is called ARTINALI. So it's going to condition data changes on events as time events. There's we show in the paper this is equivalent to learning data, event, and time. It's just base probability. And what we end up doing is, we end up deriving data per event invariance, time per event invariance, and data per time invariance. So all these three together, we can leverage and say, okay, this data has to change in response to this event at a certain time. So that's the idea. So we built this system called ARTINALI, where you give it the program under test. So you still have to log the events yourself. This is common to many of these other event logging systems as well. So, but in theory, we could have built a front end to do that automatically. But once you do the log, everything else is automatic. So we'll derive the data per event, the event per time, and then derive the data per time, and then feed this directly to the intrusion detection system. So it will use these invariants and look for violations of them to detect an attack. So we evaluated this on two platforms. So one thing I should mention here is, there aren't that many open source. So we try to pick open source systems so that we can try to find security loopholes and evaluate it on our system. This is not a requirement, but it just makes our life easier in terms of evaluation. So there aren't that many open source cyber physical systems we could use. So we found two. One was an advanced metering infrastructure called SegMeter. So this is a real smart meter, and we can actually look at the code. It's running a Linux-based variant, and we can run our system on it. And then there's also a smart artificial pancreas. It's an open source project for people with type 1 diabetes when they have to have a control loop to monitor the insulin levels and so on. So these were two systems that we used to test our evaluation. And what we did is, so we took this cyber physical system, generated a whole bunch of traces, just normal operation of the system with different events and so on. And then we had a learning phase where we took some traces, learned the invariants, and then we also had the intrusion detection phase where, as the traces were being generated, they were fed to our intrusion detector, and if it violated the invariant, we would raise an attack flag. To keep the comparison fair, we compared with three other systems: DICON, Texara, and Perfume. So these systems do not have the data, the time constraint. So they look at data over event over time, and so on. They don't look at data, event, and time that ARTINALI does. So and then we seeded the invariants from each of these systems in turn, and then checked how good they were at detecting the intrusions. So we wanted to make it an apples-to-apples comparison. So any trace that we got, we ran it against all the invariants and checked which of them would actually detect the security attack. Yes,
So, what was the load you had on the device to get the traces in the first place?
So you mean what did we actually do? Or?
What was the input that you gave it to generate these normal operation traces?
So for the seg meter, we just let the meter run for a day, I believe.
Okay.
And it was generating these traces every time. Well, when we randomly sample at different points of the day. It was hooked up to a real,
real power
power source, right?
Okay,
and communicating with the server.
Okay.
With the open apps, we didn't have a real insulin pump or equation, so we used some data that was released by the National Diabetic Association to simulate different conditions of typical patient behavior, and then ran it with that. So this is what they recommend that you use to test the system in operation.
Yeah, I guess it's a challenge if you're going to do intrusion detection to have a sense of the variety of in the wild, what the kind of behaviors these things are going to see, right?
Right. So one thing we don't need though is a set of attacks, right? Because we're characterizing the good behavior of the system.
Good behavior.
Yeah, but you're right. That is going to be a challenge. Yes.
Yeah.
So you must have some time lag. You must need to see some amount of the trace before you start saying that an attack has been detected. Because I mean, the very first.
Yeah, you can't detect it, right?
You're going to say, well, my invariant's 3, right? And then the next one's 5, and you're like, whoop, that's an intrusion, right?
Yeah. So okay, and for the purpose of experiment, so we haven't actually gone and measured what that time needs to be to get a theoretical bound. For the purpose of experiment, I believe we ran it with like 50 traces. So however long, in the case of the smart meter, that took about an hour to generate. In the case of the insulin pump,
full traces, learn the invariance, and then on the next trace.
And the next trace. So we partition that set, and I'll show you how we. But you bring up a good point, right? So you can make these intrusion detection systems be very how to put it, like you can have very high recall by just tuning the parameters appropriately, and we tried to be balanced. I'll show you how we did that. Yes.
Is the goal here to come up with a universal kind of intrusion detection, or per meter?
Per system intrusion. So
I mean, per family, you have an intrusion detection system which is trained using the.
So for a particular meter, let's say, right, you run the intrusion detection, you run the invariant generator, and then feed it to the IDS. So for that meter, it will go and monitor stuff, because there are thousands of.
Family, and then if Mike's family, he
has to run the training.
The training.
Yes, at least that's the model we're using now. Having said that, for a particular class of devices, we don't believe there'll be that much variation, but we haven't explored that. So that's an interesting question, right? How much cross learning can I benefit from? Right? And here we are learning it for a particular system and trying to detect intrusions on that system. Yep.
So is there a notion of, in terms of this training phase, the notion of coverage in the sense?
I'll talk about that.
Okay.
Yeah. So, you mean coverage of the inputs?
Yeah, exactly. Right. How do you know that you've seen all the things that are normal?
So we don't, but we do measure false positives and false negatives, right? And we can look at how to balance those two. So yeah, but the assumption is that you've been able to see all the behaviors in the first few minutes of training, which will impact a false positive rate. So I'm going to show you the data. So the first thing I want to say is, when we built a system like this, one question is how do you evaluate it? So we tried to come up with attacks ourselves on these meters and the smart APS. So this is by its definition, it is anecdotal in the sense we tried to take attacks that other papers have discovered on these class of systems and try to replicate it in our lab, and we were able to do it. And in this case, we were able to actually detect all the attacks that we targeted. But this by itself is not sufficient, right? Because one of our goals was to detect zero-day attacks. So yes, this is a low bar to meet. We took a bunch of attacks, we mounted them, we detected them, but it's by no means enough because an attacker can do arbitrary things, right? So how do I emulate that? So one thing we tried to do is we tried to emulate what an arbitrary attacker would do by using fault injection or mutation testing. So this is where in the absence of data about exactly what an attacker would do, we have to make worst case assumptions and say, all right, if an attacker somehow manages to flip a branch or somehow manages to mutate the value, am I able to detect that with my assertions? So for example, here we did data mutation at different kinds of pointers, for example, at integer values to emulate integer overflows and so on. We did branch flipping, so we said instead of going down the if path or then path, you go down the else path, or we tried to introduce delays at random places. So when I was here last year, I spoke about this project where we had a model checker to go discover attacks against smart meter. So one of the things we found that the model checker found was even by delaying synchronization between the server and the meter, you could actually introduce attacks. So we tried to use that knowledge of the kinds of attacks that could occur here, but we had to do this in a sort of blind way to be unbiased. So we did a bunch of these mutations. I forget the exact number, that's in a paper, and tried to get statistical estimates of how many were detected and so on. So now we come to the important question of false negative versus false positive, right? So depending on how you tune the IDS, you can have more false negatives or false positives. So I'll spare you the definitions of these. But what we tried to do was we measured what's known as the F score. So it tries to balance the false positive, false negative. It's a standard term in information retrieval. So there's this parameter called beta, which lets you choose which one to prioritize more. So if you have beta greater than 1, you'll prioritize false negative higher. So you want fewer false negatives. Beta equal to 1, they're equal, and beta less than 1 is the other way around. So for the smart meter, we said, the worst case that happens if you have a false negative is you lose some money. Somebody steals your power. So it's probably not as bad. But you don't want false positives, because if you're a utility provider, you don't want to come look at a false alarm every few minutes, right? That's a cost. So there we prioritize false. So we said we'll let a few false negatives slide, but we'll prioritize false positives. For the medical device, we did it the other way around. Now that's you could argue both ways, but our rationale was you don't want an attack to slip through, even if it means alerting the human every now and then. It's probably fine because you're wearing the device. So here's one example of what we of the kind of tuning we did. So the x-axis is the number of training traces. The y-axis is the percentage for different false positives, false negatives, and F-score, where they're both balanced. Okay, so here you'll see, and for the different F-scores. So this is for the open apps. So you'll see that the false positive rate keeps decreasing as you increase the number of training traces, but your false negative rate might increase, but it also stabilizes at some point, right? Because you're going to reach saturation. Now so this is for one particular IDS, that the one we generated the ARTINALI invariance for the platform. So we can find the optimal number of training traces that maximize F score, which happens to be around 15, or you could go higher as well if you chose to. But the important thing is this kind of training is very platform specific, very IDS specific. So we had to do this for all the IDSs, for all the platforms. And what we are going to do is, so for every system, be it Texada or Dicon or Perfume, we try to find that point at which that particular value of F score is maximized. So that's the best configuration for that system. And then we compare it to the best configuration for our system. So in a sense, we're looking at the best case for each of these systems. We could have done it for average case and worst case as well, but it's important to make sure they're all on the same even keel. So first, let's look at the false negative rate. Here we are looking at the tuned values. So there's 95% confidence interval. So we looked at different kinds of attacks or arbitrary attacks, data mutation, branch flipping, artificial delays, and so on. And one thing you see is with the other three systems, the false negative rate for, first of all, it varied depending on the kinds of attacks you were generating. So an example would be Dicon was very good at detecting data mutation attacks because it was using data invariance, right? Whereas Perfume, for example, which was looking more at the timing of events, was very good at detecting artificial delays. But ARTINALI was good at detecting all the three because it was looking at the intersection. So it was looking at data, event, and time. So overall, the false negative rate with ARTINALI, our system, was much lower than the false negative rate with each of these systems. The white bars are the aggregated false negative rates. So in fact, it's about 2%. So that means only 2% of the time we miss the attack, whereas with some of these systems, it could be as high as 90% or 50% on average. So again, this is just because we are able to say specifically at this time, at this event, here's how the data value should change. So an attacker has very little freedom to change things and get away with it. The story is not, however, as sanguine for the false positive case, though we end up doing better than the other systems. So here, if you look at Dicon, Texera, Perfume, the false positive rate is pretty high. In the defense of those systems, I'll say they were not meant for security or intrusion detection. They were more for software engineering. So they had a programmer look at the invariance. So for them, a false positive was fine, as long as a programmer could invalidate it quickly. For us, we don't have that. But even so, our false positive rate was about 12%. So we were still improving on those other systems, but we still think this is pretty high. So we do need to bring the false positive rate down. But I'll tell you this, one of the things that brings the false positive rate down is the chance of a coincidental path where the data, event, and time exactly match the correct one is actually lower, because you're looking at 3 things as opposed to any 2 or just 1. So we could do better if we actually started subclassifying the kinds of paths the software was taking. For example, which we don't do. We just learn it as one aggregate thing. For example, if I say, whenever the smart meter communicates with the server, I'm going to learn one kind of invariant. And when it, starts sensing the power values, I'm going to learn another kind of invariant. Now, this will require us to customize the invariant generation system. We try not to do that, but that's one way we can bring down the false positive rate. But even without doing all that, we're still doing better than these other systems, but there is room for improvement. And of course, the big thing is performance, because performance and memory, because these systems are very resource constrained. So it's the results for the smart meter platform. We have about 4 megabytes of memory to use, because the Linux, it's 16 MB RAM, and then the Linux image and other things take 12 MB. So that's the limit we are operating under. So one thing is, all the systems end up being about similar. So the invariants being stored are about 3 megabytes, which is still less than that. But even in the worst case, Perfume still is less than 4 MB, so it's fine. The more important thing is the detection time. So there's performance overhead. So we impose about 33% overhead, which is also comparable to other systems. But what does this mean in reality? So in the case of smart meter, it's sensing the power values, taking some action, sensing the power values, and so on. This loop happens every 1 second. So you have to finish whatever your IDS does in that it happens every 1 minute. So you have to finish whatever your IDS does in that minute. Otherwise, you won't be able to keep up, right? And we find that we can finish within the first 10 or 15 seconds. So that's also the detection latency. So as long as we are within that minute, we have more room, for example. Yeah.
So what are the assumptions about the other load on the CPU when you're doing it?
So we are running whatever load the manufacturer or processor
I see, so it's in addition.
So
it still takes
that's already there. In the worst case, but our overheads are still, we are within like 25 to 30% of the time. So there is room to actually have, even if this is certain workload for whatever process we're running, it should still be okay. But having said this, these are not data centers or clouds. Right? I mean, you're probably not running very compute-heavy stuff on it. So that's the other side of it. But we are able to make sure that whatever load we impose, it doesn't affect the real-time performance of the system. So for these 2 systems. So to summarize, ARTINALI is a multi-dimensional model for cyber-physical systems. We capture the data event time interplay, and we have real-time data invariance. Here, when I say coverage, I don't mean coverage in the form of test coverage. I mean coverage to different attacks that we introduce. So that increased, and it decreases the rate of false positives, but there's still room to improve that. And the overheads are comparable to other invariant detection systems. But the goal I want to emphasize is, not that ARTINALI by itself is a panacea. There's still room to improve it. But the idea of applying dynamic invariant detection is important in these domains, because you can't have programmers go write specifications for you. So, and these embedded systems do very specific tasks. So I think there is a lot of opportunity here in terms of coming up with generic invariant detection systems that can learn automatically without the programmer having to describe or write specifications, and then to feed these back for both security as well as reliability. And right now we are actually trying to run this on a UAV. So we have a drone that we are trying to attack and prevent the drone from crashing just in time by running ARTINALI, but that's still work in progress. So, yes, of course.
So you're saying you had that it took 19 seconds, right?
Yeah.
And the time was, you had a minute, right?
Yeah.
So it was 19 seconds for all the processing that it did, and then the processor just sits idle for the rest of the time?
Well, no. So sorry, there is a workload that's already running.
Right.
That's the event loop, and things happen in that 1 minute. Okay, so it reads the values, it does some calculations. Sometimes it just sits idle and so on. Our IDS is running in a parallel process. So it's running in a separate process. Separate process. So it uses a pipe to communicate.
Another processor on the device.
We need another process. So it's running standard Linux. So it's scheduling our tasks.
Yeah, but I mean it changes the cost of the device. They have two processors. Right?
No, it's one processor,
Okay.
but running two processes.
Oh, two threads.
So we are
Okay, yeah.
right. It's a Unix process, right? So we communicate with
That's
pipes.
what I'm saying. So the competition might make the other process miss its deadline.
Right. So we didn't observe that. So we in all our tests we never missed the deadline.
Okay.
So that's so you're right. I don't have a proof here that we will never ever miss a deadline.
I don't really know how close you were getting, right?
Right. But empirically, and we finished our IDS process in the first 20 seconds of the minute we have. So that leads me to believe we are not. I'd have been worried if we had finished at the 59th second, let's say.
Yeah, I mean, it depends on how close the rest of the processing was to the deadline in the first place, right? Because if you're, it's the same thing as co-scheduling stuff in a data center, right? You have to worry about the interference, right?
Right, I agree with you. I mean, one thing would have been nice to do is to say, I can bound the amount of overhead I introduce with this. But I will say this, however, we can prioritize which parts of the code to monitor. So we can, if we find that we are close to that brim or we are going to overflow our time, we could say I'm going to monitor fewer invariants. So of course you trade off coverage. So we had another piece of work where we were trying to model this as like a set cover problem. I have a property I want to establish. What is the minimum amount of invariants I have to monitor to establish that property? And you can treat it like a integer linear programming problem, right? But I agree with you. I mean, what we have is a more anecdotal demonstration that it doesn't affect the real-time operation, but it would be nice to have a proof that it doesn't. Any other questions? So I'm going to tell you a little bit about some of the ongoing work in my group and then conclude. So I spoke about some of the work we did on formal methods to use model checking to find attacks against the smart meter. So we had this high-level model of the smart meter in mod or rewriting logic. Then we ran the model checker and it found a lot of real attacks. So I spoke about this last time I was here, where we had things like you could tamper with, say, the communication between the two boards. So this is a commodity smart meter we bought off eBay. So it has some protection but nothing major. So you can easily open it up. And we could do things like we connected a timer which would send a pulse to the meter exactly at a certain time and reboot it. And 9 times out of 10 we wiped out all the data that was stored on it at that time. And so the model checker found many of these attacks, but what it required was this high-level model of the CPS. So we're now trying to see if we can do this without having the programmer write that high-level model. So we're trying to model these attacks directly in the code as symbolic execution, through symbolic execution, and then we're going to try and use these invariants with the model checker to show that the invariants are sufficient for establishing a certain property. So this is still work in progress, but that's the goal, right? So ultimately, we want to have a system that comes up with these specific these invariants, and then automatically the model checker goes and tries to find attacks, and then it finds an attack, let's say, and then we come up with new invariants to detect the attack and so on. So to have the self-improving capability in IDS, but we're not there yet. Another recent project we started in my group is trying to build smart middleware for IoT devices. So while we've done a bunch of work on JavaScript for the web, there is a lot of effort to run JavaScript on IoT devices. So Samsung, Intel have VMs that actually run JavaScript VMs on tiny embedded devices. But today, to program these, you still have to program them on a device-specific basis. So our goal is to try to come up with a framework for programming IoT devices so that you write JavaScript code in one place, and the framework takes care of distributing the computation, sending the chunks of code, migrating them, scheduling them, and so on. So we call this Smart.js, but the name may change. So we have some examples of code that we can migrate on the fly without requiring the programmer to do anything. So one of the challenges here is keeping track of closure state without modifying the VM. I'm happy to talk about this offline if anyone is interested, but this is a recent project we started. And more broadly, going back to the DNN case, I think what this calls for is we need to think about resilience of machine learning applications. So today, the problem is, there's a lot of work on adversarial machine learning where you change inputs and so on. But what if you are able to change the actual parameters of the ML algorithm or change the implementation or the hardware that runs it? So what we want is to build algorithms that are resilient to perturbations, even of the parameters. So for example, if you have, say, an algorithm which goes off on a different path for a small change in parameter, that's not a very resilient one. So can I build machine learning algorithms or machine learning systems where a small change doesn't introduce large changes in the output? So this is something looking at with a bunch of the theoretical machine learning folks, trying to see if we can bound the algorithmic resilience of these systems. So to conclude, I hope I've convinced you that cyber physical systems, resilience and security are important challenges. So we looked at two systems in this context: deep neural network accelerators for self-driving cars and invariant monitoring for embedded system security. In this future work, we want to do formal analysis to actually prove properties about these systems in the presence of our mitigation mechanisms, as well as build smart runtimes for these to help programmers write resilient code. And finally, interested in looking at resilient machine learning algorithms as well as systems in the broad sense. So with that, I'm happy to take even more questions, and that's my email address there in case you have more questions. Okay, thank you very much.
So when you use formal analysis model to do CPS safety, the adversary model is different, right? Not bit flips.
It's not bit flips. So thank you for that question. So here we are assuming an adversary that can tamper with the physical interfaces of the system. So I'll give you an example. So you can reboot the system at any point in time, let's say, right? Which is straightforward. You just plug in, plug out. You could read the so these meters have a serial port. Okay, you can plug a serial port cable and read the data. So that we assume that even if it's encrypted, it doesn't matter. The meter will register the data as being read. And the third attack there is we can drop certain messages sent to the server. So I can drop all the timing synchronization messages.
So the device is temper resistant.
It is not.
It's something very deep in the chip.
Well, we assume that, okay, so we assume that the attacker is not like a nation state or someone who has deep pockets, right, to go and do the kind of thing like where they reverse engineer the whole chip and so on. What they can do is they can tamper with the physical interfaces, which is, so all the stuff, attacks we mounted, we bought the equipment off eBay like for less than $50. So a solid state timer costs $10, for example. So you can actually hook it up to your meter and send the reboot pulse at the right time. But the model checker said that you have to reboot when you come to this function in the code. And then look, the meter loses data. So that's, but from that to actually translation to the physical attack was straightforward though. So I don't know if I answered your question, did I?
Yes.
Okay. Right. So all the attacks there are done on the real meter with equipment bought off eBay for very low cost, which is what we assume the typical attacker would do.
So, you talk about the modeling and whether or not you're not expecting people to build these models of the system. Developers, right?
Yeah,
Discover. But how do they get it right if they don't have a model to begin with?
Yeah, that's a great question. We've talked to some companies that do these, IoT device development, and the feedback we got was they start with a model, but the code evolves and the model is often updated. So you're right. So many of these devices are, well, they're glorified state machines, right? So you do have to have a model of the device, but by the time the code goes through iterations and it's ready for shipping, they don't necessarily keep the model up to date. So in fact, when we were trying to pitch it to a company that does IoT device development, and the feedback we got is we can't rely on their model. So we initially started off by saying, give us your model, we'll turn that into invariance. But then because the model turned out to be not accurate, we said, can we learn the invariance directly from code? But you're right, if there is a...
So if they use the language like P, this work that Shaz worked on, would that have been a good input? It seems like a possible input to your...
Absolutely. So in fact, for the formal modeling work, we assume the programmer actually expressed the code in a higher level model, rewriting logic. And I don't know the specifics of P, but from what I know, I assume it is a high-level logic to express your program in the CPS program. So yes, certainly we could do better invariants in that case, and you don't have false positives. So this is just my personal take, right? So many of the programmers we spoke to, at least who were on projects, they were not necessarily CS majors. Many of them had engineering backgrounds, but few of them had formal methods or were able to describe the program at a high-level logic. So they were writing direct C code.
But you were saying that they were expressing as a state machine.
On the board.
Yeah.
On the whiteboard.
Okay.
Sorry.
I see. Okay.
No, not actually.
I see.
So they gave us some sheets of paper or UML diagrams in some
Yeah,
cases.
I see. Okay.
But they had a model, but not actually as not the way a CS person would think of as a model.
Okay.
Right.
Interesting.
So yeah, but maybe it was just this one or two companies we spoke to. Maybe there are other companies which actually do a more diligent job of this. So.
But I remember the beginning of P was Windows developers would join the state machine on PowerPoint or something.
Yeah, it's
Visual.
Visual. But yeah, it's the same story. Except they had such a big thing, it couldn't fit on a board.
Right.
So.
I mean, I know there's been a lot of work on model-based code generation in the software learning community where people would say, okay, let me express the state machine, I'll generate the code automatically and so on. I don't know whether those tools are actually used in these.
He is being used.
Okay.
It was used in the USB drivers. It's used in Azure. So.
Oh, I see.
It's actually, it is a real thing. Yeah.
Okay, I would love to learn more about it then. Thanks.
Okay. Thanks a lot.
Great. Thank you. Thanks, everyone.